Okay, the record is now on. So, I thought I planned it well to begin the example by using the H shape, but I think I realized that I should have done this before. So my apologies, sort of the script was not good, say that. So before we begin, we should try to calculate the elastic section modulus and the plastic section modulus of AD rectangle, just to show you how things are. So let's say this is the width B and this is the depth D. Okay, now you know for the elastic, you are let's calculate the major axis, okay, which is X. Okay, so you know the Ix is going to be equal to BD cubed over 12. And therefore the Sx, which is Ix divided by C, that's going to be BD cubed over 12 divided by D over 2. Correct? So that is the D is gone. That is 6. So this is a typical formula for a rectangle. The elastic section modulus is BD squared over 6. And you'll find yourself from time to time using this formula to calculate the elastic section modulus of some sections when you design it. So it's good to know it. So now it comes down to plastic. Okay. When in plastic, remember from the formula, we are taking the moment of the area around the plastic neutral axis. And we also know that this is the symmetric section. So elastic section elastic neutral axis and plastic neutral axis are essentially at the same location. Okay. You can do this because it's an elastic neutral axis in the middle where the centroid is, right? But for plastic, it's the same. But remember that what you need to do is you need to take a moment of the area around it. So it's this area and then that area. So there are two areas. Okay. We come back here. It means that two are the same. So I can say it's 2. The area, be careful, it's BD over 2, right? It's half the depth now because we need to take moment of the area. And the moment arm here becomes D over 4, right? So now you have B to D, so it becomes BD squared, 2 are gone, over 4. Now compare to BD squared over 6. Now remember, this is a rectangle. So the shape factor of any rectangle, it's Cx over Sx. Basically, it is 6 over 4 or 1.5. So that's a shape factor of any rectangle. Now, yesterday we mentioned that for the H shape, the shape factor is about 1.1 to 1.18. That is because we don't build the solid section like this. It's very heavy and very, say, inefficient in terms of moment of inertia and the use of the material. So we do not get the shape factor as high as this one, you know. It's only 1.1 or 1.18, but that is okay. To have this, you know, and to sacrifice material to form the solid shape like this is not very economical as at all. Okay, so that's the shape factor that we should get, and this is the basic formulas that you can always use if you have a rectangle. BD squared over 6 for elastic section modulus and BD squared over 4 for plastic section modulus. Keep in mind that when you calculate this Zx yourself, you need to split the area into 2 areas and then take the moment about plastic neutral axis, right? But after that, you get the formula for any rectangle. That means if you have a rectangle, you don't have to split the area into two. Again, you can use this formula right away. That's the point. Okay. So now we come back to the example that we worked on yesterday. Now, when we calculated the elastic section modulus and plastic section modulus in y-axis, you see what happens? Essentially, we got the shape factor equal to 1.5 because in y-axis, if you look closely, you see that we are doing nothing but bending these three rectangles, put together. See, each one of them does not have any benefit from being away from the neutral axis or CG of the section at all. All three elements lined up exactly where the centroid is. So you don't have the AD squared term at all. So essentially we are, bending a series of rectangles here. That's why the shape factor is 1.5. But keep in mind that even though we got a large shape factor here, the plastic section and elastic section moduli, it's a plural form, right? They are quite less than what we have from the major axis. Okay, so that should clear this up. And now I am left with just another example to demonstrate the another problem. Now this one, ooh la la, just what x-axis will be enough. Now you need to locate the centroid, right? Or elastic neutral axis. You say this is centroid. And plastic neutral axis. Okay. Now, do I need to show you how to locate the elastic neutral axis? Do I? Oh, quiet. So I don't think I need to. If you don't say anything, I'm just going to give you the numbers right away because this is like kid stuff. The total area is, I'm going to work in centimeter unit. So it's going to be 12.5 multiplied by 2.5. That's for the flange. And this is the cut T. So we don't call this the web, okay? If it's cut T, we call this stem. It's called a stem. For the angle, we call it legs. For the H shape, we call it the flange and web, okay? So here is 20 multiplied by 1.9. Oh, keep in mind another thing. I haven't told you this, but this is a good time to tell you. When you encounter the situation where you need to select the size or the thickness of the plate, generally I should write somewhere, the plate availability in the open market where you can order things, it comes with the increment of 3 millimeters. That means you can easily find a plate of a 3 millimeter stick, then 6 millimeter, 9, 12, 15, and 18, and so on. Okay. Try to increase the plate thickness by the increment of 3. And this should be easy enough for you to find in the market. And the maximum size that is generally available would be about this. I'm not sure. I'm pretty sure you may be able to order things different from here, but you need to order in a kind of big lot. So general size of the plate is 1.5 meter by 6 meter. Okay, I know this because I used to design the fuel tank, the huge one, for the oil company. long time ago. I don't remember if I designed it, but maybe it wasn't built or anything like that. Kind of a relief in a way. Anyway, so when you want to build that, you have to order the plate 1.5 by 6, and then you put them together to form a tank. So like this, it's like a brick wall, but instead made of 1.5 meter by 6 meter, like this. Okay, keep going. And the thickness that you should order, after you know the thickness that you should use from the design is with the increment of 3. Okay, so let's come back here. You see that this is a very old example. I try to match the number I have in the US. So it's not good in terms of practicality, because 19, if you really want to order a 19 millimeter plate, people is going to scratch their heads like, why? I don't have it, man. Either you're going to go for 18 or perhaps 20. 20 is like a universal number. So possibly you may have 20. Okay, but before 20, it's an increment of 3. Or if you're not sure, you can try to ask around, see if this plate thickness is available. That is a part of your job, because if you design something and then the materials cannot be found in the typical market, you're going to create a lot of headache for construction. And you can be irresponsible saying, hey, it's not me to worry about it. I already designed it. I don't care. You have to match my drawings. Then you could probably do that, but someday your reputation is going to go around. It's like, this guy just someone that you should not cooperate with. And believe you me, the engineering community is not that big. Everyone knows everyone. If you are going to have the reputation that precedes you, it should be a good one rather than a bad one. Okay, so that's it. Say this is not a very practical number, but for the sake of example, I think we are fine for now. So this is about 69.2 square centimeter. And because you don't say anything, so I am giving you the Y bar right away. The elastic neutral axis is here. So for ENA, Y bar is 15.02 centimeter. So now our job is to find the plastic neutral axis. This Y bar, the elastic neutral axis, is like kid stuff. You've been doing it since your first year, second year. Okay. But now, because we are using the same material, so that means to locate the plastic neutral axis, we just try to divide the area of the cross section into 2 equal parts. Okay. So now the question is, let me expand this. Where would your plastic neutral axis be? It could be in the flange or it could be in the stem, right? So how do we know that? We are going to have to make assumption, right? If we don't know where it is. But sometimes you don't need to just go ahead and try to flex your muscle in mathematics. What you can do is just to compare these 2 areas, right? So let's call this A1 and let's call this A2. So A1 is the first term, right? 12.5 multiplied by 2.5. And the A2 is 20 multiplied by 1.9. This is easy. So it's 38 square centimeter. Now, because we have the total area, you can see, oh, this is more than half. So A2 is greater than 1, correct? Hey, you guys with me? Hello?
Yes.
Okay, so A2 is greater than 1. So if you are going to split the area of this T section into 2 equal parts, where would the plastic neutral axis be? In A1 or in A2?
A1.
Huh?
A1.
Yeah, but A2 is greater than half of this, no?
A2 ครับ sorry.
Right, so because A2 is greater than A1, so to have the axis where it breaks this section into two equal parts, A2 would have to give some to A1, correct? Let me give you the number. This is 31.25 square centimeter. So obviously, the plastic neutral axis must be here. By inspection, since A2 is greater than A1, TNA should be in the stem. So now we are going to have to do some calculation, right? So let me say this is the distance called YP, okay? Now, that means the thickness 1.9 of the stem multiplied by YP. That would be half of the area, correct? You can set it up like this. This should be equal to 31.25 plus the length of this is 20, right? 20 minus YP and multiply by 1.9. Or you know what? After more than 10 years, I just realized that I could actually set this up, right? 1.9 YP must be equal to 69.2 over 2. I can actually do that, right? Pretty easy. Just it has to be a half of it. Wow, been stupid for some time. So YP here is going to be equal to 18.22 centimeter. Okay. Now I don't know where it is. I seem to have lost the page following this. So every year I have to calculate this thing again. Which I really don't mind, but it seems a bit absurd. Yeah, that's what it is. Okay, so here we go. I'm not gonna do the elastic section modulus because that's a piece of cake. So let's do the plastic. Now be careful. Now you know this is where your plastic neutral axis is. Now you are going to have this area where you need to take moment about PNA, okay? And then you are going to have this area. That's another one, and then that's another one. So 3 of them, and you cannot use the BD square over 4. That is the 4 basic rectangle where the PNA is right there at the centroid. When you face something like this, you need to calculate. No two ways about it. So CX is going to be, the first one is 31.25. That's the area, okay? And the distance would be, if YP is 18.22, that would have to be the, you know what, this is confusing, but we already passed this one, but I have to do something because A2 here is the entire area, okay? Let's put the color back. Okay. If that's 18.22, so that is 20 minus 18.22, which is 1.78, right? So that distance is going to be 1.78 plus half of the thickness, which is 3.5/2. The next one is, now it becomes the area multiplied by the moment arm. So basically it's, you know, the width multiplied by the height and then the height over 2, right? So I can easily do that. So it's 1.2, 1.78 square over 2 plus 1.9 and then 18.22 square over 2. Okay, so then that's it. I don't have the number. You can punch a calculator for me if you don't want to, or we're just going to leave it like that. Okay. Is there any question? Is there any question? Wow, all quiet. You know, let me check this. The timetable. Now we are completely finished with this, and we are, you know, we are pretty quickly, and I can begin the design example, but I don't really wish to. But you know, if we go about it very quickly, it's going to be quite beneficial for you in the end. So what would you like to do? It is not a bad idea to talk about additional failure mode now as well. The beam is going to be shear. So would you like to talk about that now maybe? Before we talk about your project? Because we have quite a few minutes left. No response. So let me talk about this for 20 more minutes, okay? Now we are done with, oh yeah, actually, I forgot to do this, right? We talk about plastic section modulus, and actually we need to talk about the beam as a whole as well. So let us do that, okay? Now, let us summarize what we've been doing since yesterday. Now we talk about the flexural members, okay? The first step, Nakarin, why are you sweating?
ไปกดโดนครับ
Huh?
ไปกดโดนอาจารย์
Oh, okay. Anyway, say we're now looking at the flexural members, and the first step that we do is we make sure that it is stable. So we begin with the beam that is stable, and we call it the laterally supported beam. And the beam will reach its maximum flexural capacity when it is laterally supported. But when the beam reaches that capacity, I can draw it again, that your section this time will form a plastic hinge, and the stress distribution we use will not be the elastic one, it will be the plastic one, okay? This is the plastic stress distribution, which leads to the plastic section modulus of the section, the Z. Okay, and we also mentioned yesterday that the Z in the typical catalog is unfortunately the elastic section modulus, but Z in my table, that's plastic. So use the right one, okay? Remember that the plastic section modulus can be picked up from this table, there and there for both axes, okay? Now let us go back here, and it's you know, again, just like compression member, there are two things to consider when we talk about this flexural member. Okay, first, if the member is laterally supported, we are going to reach MP. That's the global buckling, the buckling of the entire member. Okay, it's safe that, but again, we need to consider the fact that because it has flanges and web, so chances are if the flange becomes slender or the web becomes slender, they can buckle before your beam reaches MP. Okay. So now it's local buckling again, just like in compression member. So we can say this is the one that may prevent the beam from reaching MP. Okay. In compression member, if you have the local buckling, say because either the flange or the web is too slender, that will prevent you from reaching the critical buckling stress F critical. And similarly, if you have either the flange or the web that is too slender, it may buckle before your beam can reach MP as well. So it's a pretty similar behavior. And that is a flange local buckling, or that's a web local buckling. All right. And when we consider this in a similar, not a similar fashion, but it's there. You have been exposed to the residual stress, and we have the residual stress before in compression member, and it's going to play the part here too. Remember that if we continue to push our beam, you can increase your, this is too dark. You can increase your strength from MY to MP, right? But if there is any local buckling problem and that something is going to happen, the residual stress will again deviate you from reaching it quickly by creating the new path, because you already have some stress there in the section, but eventually it will reach MP. But say along the way, we are not going to really have a straight line like this because of the residual stress. It's going to have some deviation. You know, it will reach MP, but it's slower. So this is going to be the design curve of the local buckling stuff. Well, it's slightly different from the compression member. Well, actually, in compression member we don't talk about it, right? But anyway, for the local buckling in your flexural members, there will be 3 sets of behavior, and when we have 3 sets, 3 zones, generally it means that you now have 2 limiting values. Okay, we call that lambda P and lambda F. Lambda R, I'm sorry. The P is F. Where does F come from? Lambda P. P is for plastic, I suppose. And R, that should be for a residual. Okay, so to speak, when you compare the slenderness ratio of the elements in your section, if the slenderness ratio is less than this limiting value lambda P, you are going to have the beam that can reach MP or plastic behavior. Okay, if the slenderness ratio of your element is greater than lambda p, but not lambda r, you will fall into the second zone where the behavior of your section becomes inelastic. Okay. Or if you now have the element with the slenderness ratio so large that it also exceeds this limit, you will fall into elastic behavior. And now you should know what it means, right? Elastic, you only put a small load in it, it buckles already. Then you unload it and go back to normal. Not good, because in terms of load carrying capacity, it's so small. Inelastic, you're going to have some damage, right? So when you pull the load back, some permanent damage is going to be there, but the member is fine. But for plastic, you know, the entire section would give, and you know, you're going to have, you know, the structure that would not be able to be used anywhere anymore. But generally, yeah, we look for this because it's the maximum capacity of the structure that we could get. And now this is a behavior. When your slenderness ratio of the element is less than this, you have plastic behavior, and that element is called compact. Okay, it's the name. When the slenderness ratio is greater than LP, but still doesn't exceed lambda R, not LP, lambda P, but not lambda R, you have the inelastic behavior, and your element is called non-compact. Okay, and of course, when the slenderness ratio exceeds lambda R, it now becomes the slender element. Okay. Now here we are, the compact section. Now we talk about the element. A compact section is when no element in the section has the slenderness ratio greater than lambda p. So let's say if we are talking about the edge shape, it means that both the flanges and the web must have the slenderness ratio lower than lambda p for the section to be called compact section. And your member can now reach MP. Okay, that means both must be compact. Okay, and for non-compact section, either one of them, if either one of them has the slenderness ratio greater than lambda p but not lambda r, the section becomes non-compact section. And your member will not be able to reach MP. Somewhere along the line, the local buckling will occur to prevent that. If one of them becomes non-compact. Now, the last one is slender. Now it's pretty obvious. If either one of them is slender, the entire section is called slender section. And you know, this will have the elastic buckling. Actually, it will not reach MP by now because this will not reach MP, but I should say MR, the M residual, because we can see from here that if you have the slender section, you are down here and you are lower than MR. The MR is the residual moment. It's the moment that you also deduct the residual stress out of your calculation. We'll see the future. Okay. So any question? Now, in a pretty similar fashion to when you check local buckling in compression member, you now need to check local buckling in the flexural member as well. But you see that the limiting values are different because the stress is different. In compression members, you have the uniform axial stress. Here you are going to have the flexural stress. So in order for the flange to have the compact section, lambda p is now this value. only 0.38 square root E over Fy. It's only 8 something, I don't remember the number, but 0.56 is the limit for compression member, right? That's 16. So this is not 8, it's just gonna be 10 something, okay? And the non-compact lambda R is just square root E over Fy. Okay. Now Nakarin can see the we have a cases put in a numerical order, but you see this is for something like the build-up section, so it's more complicated. That's why I don't want to talk about it. For now, I think you guys are okay for this case number 10. All right. We have weak axis, which is the same limit. And I don't have to say this because we already mentioned this, that the flange is the unstiffened element, right? And now the next one is the stiffened element, of course. And the most important thing is, of course, the web right here. This is, I don't have the header with me. That's lambda P, that's lambda R. Okay. Stiffened element here, that's lambda P and lambda R. And this should be enough for you now. Notice how high this is because of the fact that in your web, you have both tension and compression, right? So it's like a double curvature thing in there. So it becomes quite difficult to buckle the web of flexural member. That's why we have a very, very large limiting values here. Okay. So that means we are quite safe, that I can safely say that for, let me say if I have a plain, better space to mention that. Okay, not anymore. So for this, for flange, because of the flexural stress, you may know that just the limiting values are low. You should check it. And some, I'm not 100% sure that every SS400 section will be compact, but I kind of remember it that way. But for SM500, some flanges are non-compact, okay? No slender flange in the hot roll at all. I mean, this is for hot roll, okay? But for the web, you can be sure that every, oh, that's a wrong spelling. Every hot roll section has, right? Rectum has a compact web. But again, for the sake of academic purposes, you should always do your calculation or state that you know, okay? If the web is not compact, the calculation becomes quite complicated. And you may have to have another class to cover everything about the slenderness of the web, not for the undergrad level. But luckily, for every hot roll section available, the web is always compact. So we don't have to worry about that, but the flange you must check. Okay, so far, any question? And now for the, this is what you're going to get from the specification. Let me go through that because I don't think it's quite user-friendly. So this is it. You know, the same plot, but now I impose the formulas on the design curve. Remember, we have the lambda p, which is for the flange, it is 0.38 square root e over fy, and lambda r for the flange is just a square root e over fy. And then we also have the limiting values for the web, lambda p web 3.76, lambda r web 5.7. When you check, but now you know the web is going to be the compact section. And that's the key. I would mention this later on if you would like to know why I write this way. This is not the wrong. This is not wrong grammatically. Web has to be compact section, and our web is compact. So check this, and you know that your web is compact. But when you check the flange, you may have the non-compact flange. And let's say when your flange is compact, your nominal moment. Remember what nominal is? I hope you still do. Okay. The calculated strength is going to be MP, or simply plastic section modulus multiplied by Fy, right? But if your flange become non-compact, somewhere around here, the slenderness ratio, the flexural capacity will be dropped. And the equation to calculate this is basically a straight line. So if you look at this, you see that this distance is basically MP minus MR. So that's MR, ladies and gentlemen. MR is .7 Fy multiplied by Sx. Remember MY is Fy Sx, right? So MR, basically you have to deduct 30% for the residual stress. Okay, 30% must be taken off. So that means this term is just this length, right? This height, MP minus MR. This is MP. This is MR. So basically, this is that distance. And look at the denominator. Lambda RF minus lambda PF. But that it becomes that distance, right? So basically, this is the slope of that line, right? And lambda, that's the slenderness ratio of your flange, minus lambda p, it becomes just, you know, the location on this. If you know this location, now you know what value this is, right? Basically, that's the linear equation. Okay. And when your flange becomes slender, which I already told you, we don't have the slender flange. So when you calculate something and then you wow, my flange is slender, you must be aware something could be wrong. Now, this is the say classical solution as well, coming from mathematics. Kc is this thing, this guy, okay? And then you need to use the elastic section modulus, lambda squared. So that's the whole picture of the local buckling of your beam. And then for the global buckling, it's just MP, okay? So I think that's it for the session here now, okay? So is there any question? Is there any question? Well, let me stop the record.